Ladies, gents, this is the periodic table basics video. That's Mr. Benjamin here. Hope everyone's keeping well during this time. It is, God, I don't even know what day it is. March, let's say 22nd. And currently all over the world of 2020, we're dealing with the coronavirus. Hopefully we can look back at this time and maybe laugh at it. I don't think that's the right way of saying it, but hopefully this will all pass. Now, this video is specifically being made for my grade 9 students in Ontario, but the information is relevant for anyone who wants to learn more about the periodic table or kind of review the information. If you don't know what a periodic table is, well, it's right here. Learning goals for this video, we're going to read the periodic table. Now, it sounds kind of basic, but there's a lot of information going on. So there's the atomic symbol, the atomic name, mass, groups and families, states. There's a whole bunch of things going on. So we're going to define those key terms. So all these ones here, plus more. Plus more. And that's not all! Exclamation mark. Last thing we're going to do is calculate information using the periodic table. So, basics. Periodic table of elements. Keeping in mind what an element is. Anything that's on this periodic table is an element. Okay? So the most basic one, the first element on the periodic table, is hydrogen. Most of the universe is made up of hydrogen. All of our stars are made up of hydrogen. The sun, for example, it's a whole bunch of hydrogen at any point being fused together, and when it fuses together, it ends up as helium. 2 hydrogens equals 1 helium. But that's not necessarily mathematically correct, it's just a way of looking at it. I'm going to erase all of this because I need to write something else that's very important. So keeping in mind these are elements, something like this, H2O, which is water. I always tell my students, if anyone can find water on this periodic table, I'll give you $1,000. Because water is not on the periodic table of elements because it is not an element. This is actually a compound. Compound is made up of 2 or more elements. Okay. So any compound is made up of these elements here in specific ratios. So for water, water will always be 2 hydrogens to 1 oxygen. That's just how it is. I've blown up this symbol here, and by blown up, I made it look a bit less pixelated, or more pixelated, I should say, because it has very important information. The atomic number is the first thing we see. The atomic number of hydrogen is 1. That means 2 things. It is the first element, and it also means it has 1 proton. That doesn't mean much right now, but I will define what a proton is later in the video, so you can always just refer back, but keep that part in mind. The symbol, which I will define on the next slide, I believe, future slides, the symbol is unique to each element. So in any compound, if you see H, you know it's hydrogen. The atomic weight, or mass, is made up of 2 things. It's protons plus neutrons. Hydrogen has an atomic mass of 1, which I should be referring to that portion there. It is an average, which is why there's that 0.008, but don't worry about that. It has an atomic mass of 1, so it actually just has 1 proton, because that's what we said earlier. But again, I'll go through that. Electrons per shell, we want to think about valence shell electrons, which is what we'll talk about later. And hydrogen only has 1, which means it's very reactive. Looks like a mess, looks like a lot of information, but, we'll get through it. One more thing to keep in mind, the periodic table is separated by specific, or it's organized in specific ways. One of the ways it's organized is by the state. So all of these here, the white didn't really work out. Let me outline it in yellow. All of these guys here are all non-metals, mostly gases. I'm going to do slash gases. All of the red here, these are all metals. And this yellow section in the middle that I'm actually going to outline in blue, these are called metalloids. Metalloids have properties of metals and non-metals. All right. Some key terms to define. First thing, AMU. Kind of talked about it already, atomic mass. But it's actually atomic mass units for the U. Mass. And this is made up of protons and neutrons. So I'm going to put in brackets neutrons. Subatomic particles. These make up, and I'm going to write this in red, make up all elements. There's actually 3 different subatomic particles. What can I use for this blue, I guess? Protons, neutrons, and electrons. Protons we talked about, neutrons we talked about, electrons we kind of talked about. Proton, positive charge. Whoops, spelled that wrong. So plus, and weighs 1 AMU. All right. Neutrons, these are neutral, so no charge, but they also weigh 1 IMU, or excuse me, 1 AMU. Electrons, negative charge. They weigh 1/2000th of an AMU, or nothing. So when we're considering atomic mass, we don't consider electrons. We only consider protons and neutrons. The nucleus, center of atom, houses protons and neutrons. Just write PNN because I'm running out of room here. Okay, when we start drawing our Bohr-Rutherford diagrams, which we won't do in this video, I'll do another video for it, the nucleus concept will make a bit more sense. More terms to define. Atomic symbol, we've kind of talked about already right here. Unique to each element. And this is going to be 1 or 2 letters. So for example, hydrogen, what's a good? Calcium is Ca, chlorine is Cl, silicone is Si, things like that. Atomic number equals the number of protons. So if I go back and look at my periodic table, all of these elements have an atomic number associated with them. Hydrogen we said was 1, helium is 2, lithium's 3, beryllium's 4, boron 5, carbon 6, It goes up by 1 each time, left to right. Excuse me. Plus 1. So that means as we go up, each element is adding on 1 proton. Every time you change the number of protons, you change the elements. So if I say oxygen, for example, represented by O, has, I believe it's 8 P positives, which are protons, it will always have 8 protons. It cannot have more, it cannot have less. If I added 1 proton, it would then be fluorine. Fluorine has 9 protons. If I took 1 away from oxygen, it would be nitrogen. Nitrogen has 7 protons. Okay? The atomic notation, this is symbol, number, and mass. So, for example, I'm going to use oxygen again because oxygen is very easy to do. I'll do this in whites, and I'm just going to cover up that valence shell. Oxygen's symbol is O. It has a mass of 8. It has an atomic number of 8 and a mass of 16. If I were to do, what's a good one? Let's do zinc. Zinc has an atomic number of 30. I don't have this memorized. I have my periodic table right beside me. And a mass of 65. At no point should anyone have to ever memorize this information. Always have a periodic table with you. Iron, Fe, symbol. The word for iron in Latin is ferric, I believe, ferric. So Fe comes from Latin. Mass of 56. And atomic number of 26. And we'll do one more. Let's do rubidium. Rubidium's a good one. This is 85 atomic mass and 37 atomic number. Valence shell. So this is the outermost shell that holds electrons. This determines reactivity. And again, that will make more sense when we do our Bohr-Rutherford diagrams, but it's also going to have an impact on our groups and families, which I believe is, next slide. So, periodic table, again, it's organized by number of protons, but the groups or families, same thing in the end. They are elements on the periodic table that have similar characteristics, and these are the columns. I always spell columns wrong. C-O-L-U-M-S? Question mark? Someone correct me there. That doesn't look right. Okay, it's the one that goes up and down. That's a column, not a row. Okay. First column here, these are alkali metals. These are in red. They're the most reactive. Exclamation mark. Group beside them, group 2, I'm going to run out of space here. I'm going to write it on the next page. So, most reactive. They only have one valence shell electron. All elements want to become balanced, meaning they have a full shell. So since alkali metals only have one, they want to get rid of it. They want to get rid of it really quickly, so they are the most reactive. Group 2 right here, beryllium, magnesium, calcium, strontium, barium, and radium. These are called the alkaline earth metals. These are less reactive. Than alkali, but still reactive. And they want to lose, or they have, 2 valence shell electrons. So they need to lose 2 of them to have a balanced shell, so they're less reactive. Group 17, all the way on the other side, these are called halogens. These are the most reactive gases. They are pretty much the opposite. I should put non-gases here. Most reactive, non-gas. They're the opposite to the alkali metals because they want to gain 1 electron. So while group 1, the alkali metals, want to lose 1 electron, they want to be -1. These guys want to be plus 1 electron. The last group, group 18, right here, these are the noble gases. Also known as inert gases, these are non-reactive. Reactive. And these have a full valence shell. Calculating different things. So atomic mass we talked about. This is made up of protons and neutrons. And they each weigh 1 atomic mass unit. Okay? If I look at any element on the periodic table, I will take, what's a good one to start with? Let's start off with magnesium. The atomic mass of magnesium is 24. Magnesium has 12 protons. I know this because the atomic number of magnesium is 12. Oops. Atomic number equals 12. Therefore, if I take the atomic mass as 24 and I take away 12, I get 12. What does that mean? Let me erase all that and write it up. Atomic mass subtract number of protons should equal number of neutrons. So 24 subtract 12 equals 12. A lot of people will look at this and just say, oh, if you just double up the atomic number, you get the atomic mass, but that's not true. If I do another example, if I take, let me find a good one to do here. Chlorine's usually my go-to. Let's do chlorine. Let me erase all that. Actually, I don't need to erase that part. I just need to erase this. Need some good erasing music for this period, but that's okay. So, let's do chlorine. Chlorine has an atomic mass of 35, and the number of protons is 17. So the number of neutrons is a question to us. Remember, the protons, this comes from the atomic number. And over here, I'm going to write the atomic notation. So, number of neutrons is equal to atomic mass subtract number of protons. So, N is going to equal 35, take away 17, which would be 18. Therefore, chlorine has 18 neutrons. And that is it for this video. So we'll say thank you with a happy face. And shortly I'm going to make a video of Bohr-Rutherford diagrams as well as Lewis dot structures, which will kind of explain certain things about valence shell electrons and reactivity, but nevertheless, have a great day.